Okay, the next thing we have is a short section really continuing on the same journey we've been on so far in the semester. So we started out looking at atomic structure, protons, neutrons, electrons, then going on to atomic properties, periodic trends, electron configurations. Now we've looked at different theories of bondings, and now we're going to apply those theories of bonding and what we know so far to understand the properties of different compounds, solids, liquids, gases, and the different phase changes and the different properties of matter and how they're going to relate to those atomic properties and the things we've learned in terms of Lewis structures. The first thing we have is a short review of the different phases of matter, solids, liquids, and gases that differ in their density, how compressible they are, and their volume and shape. So this is something you've seen before. One thing to note when we're looking at the different phases of matter is we're going to emphasize the fact that these phases are made up of certain particles that are going to be different depending on the type of substance we have. So sometimes the particles are atoms, sometimes they're molecules, sometimes they're ions. That's going to affect the properties. So solids, the particles are close together and vibrate in place. Liquids, the particles can move past each other. And gases take up their container. They're arranged randomly far apart, and the particles are all moving independently. But yeah, we're going to focus a lot on what those particles actually are. So in gases, we have a wide range of speeds of different particles. The molecules are colliding and transferring energy very frequently. We also have the pressure of different gases, right? So the collisions with the wall give rise to pressure. Pressure is that force per area. So more gas in a certain space gives you a greater pressure, more of those collisions against the wall. And that's one of the key properties of gases that we'll look at. For liquids, a lot of different properties here, resistance to flow, capillary action depending on whether the adhesive forces are greater than the sort of cohesive forces. So whether water forms this type of meniscus because the water sticks to the glass, whereas mercury sticks to itself rather than glass, so it makes this opposite type of meniscus. Liquids also differ greatly in their surface tension, the energy required to increase the surface area, right? So water is relatively high in surface tension, but other liquids are a lot lower. Next, let's look at the different types of solids that we'll focus on today. So one property we'll look at is whether they're crystalline, where we have regular repeating patterns with long-range order. So things like diamond or quartz, here every atom is in the exact same spot, and if I know where one atom is in relation to another, I can go and sort of move around and say, okay, this atom is here, so there's another atom of the same type here and another atom here, and so forth. It's this sort of hexagon repeating in space. In an amorphous substance, there's no regular repeating pattern. So glass, rubbers, plastics are often but not always amorphous. In this case, even though, say, each atom is making the same type of bonds, there's no long-range order, so I can't predict what's going on over a large area of my liquid. Crystals, crystalline compounds, we can cleave along those crystal facets, so things like mica or something like that, where you can sort of get a perfect cleave in the crystal. Amorphous things tend to shatter. Now we get to one of the key parts of this lecture. I would make this table out sort of by hand. We're going to have the different types of solids here. And we're going to have as different rows here, right, what are the particles, or sorry, different columns. What are the particles? And then this, how are they held together? Okay, next let's look at the 4 different types of solids we'll look at. So in each case, we're going to focus on what their particles are and how they're held together. That's going to impact their properties. So molecular solids are covalently bonded molecules held together by relatively weak intermolecular forces. So examples include argon, H2O, CO2, basically anything we would draw a Lewis structure for is a molecular solid. These are made up of these molecules, and the molecules are going to be attracted by weak intermolecular forces. Our next type of solid are covalent network solids. So this is the case where we have a solid held together by strong covalent bonds. So in this case, the particles there's not really a bunch of different particles. It's sort of one big molecule. Um, we can't really like identify distinct particles in our diamond. Maybe there's sort of atoms, but really the whole atom is held together in a very sort of strong way by those covalent bonds. And so the forces holding the particles together are those strong covalent bonds. That leads to these compounds typically having very high melting points. So diamond, graphite, quartz as examples. The last two types of solids, last two entries in your table, are ionic solids. So ionic solids are ions held together by strong Coulombic forces, right? So that's that attraction between, say, the negative chlorine ions here and the positive sodium ions. That electrostatic attraction holds the ionic compounds together. Those are typically strong forces, so ionic compounds typically have high melting points because they're held together by such strong forces. They tend to be not conductive in the solid, but conductive in the liquid, because once you melt this, these ions can flow past each other and make it conductive. Metallic solids, on the other hand, the particles here are going to be metal cations, and they're held together by an attraction to the sea of freely moving electrons. So gold here would have all these gold atoms, and then we can think about smeared out around the gold are all of these sort of electrons smeared out here, and those electrons are moving freely, which is why metals are conductive. They also tend to be shiny. Two other catchwords for metals are ductile and malleable, so that relates to the ability of us to like hammer these things out and change their shape by sort of either drawing it out into a wire or just hammering it to make different shapes. We can't do that with these other compounds typically, but for metals we can, and that's again related to the fact that these gold cations here, we can sort of move them past each other by slamming on them, as opposed to an ionic compound where it's not that easy to move. There's no place for like this negative ion to go because every ion is perfectly in its place in the crystal structure. Here I can move this atom around to a new position relatively easily by hammering on it. Okay, so here's our summary of those four types of solids. Again, I'd highly encourage you to sort of copy this out into your notebook with the key information. Molecular compounds are these molecules. Those are the particles held together by weak intermolecular forces. That leads to typical low melting points. These are going to apply to anything with a Lewis structure. Covalent network molecules or covalent network substances are held together by strong directional covalent bonds. This makes them have high melting points and makes them hard and brittle because those covalent bonds, we can't move the particles past each other very easily. So these you sort of just like need to know it when you see it. Graphite, quartz, any of these other things where there's extended bonding and you can't pick out the specific small molecule that you can draw the Lewis structure of. Ionic compounds, we're thinking about cations and anions held together by strong electrostatic forces. It typically leads to high melting points because of those strong forces, and it's only conductive in the liquid state. Cations and anions, right? The typical cation would be a metal, and the typical anion would be a nonmetal, as sort of shown in that next column. But we do have a polyatomic ion, NH4+, that could also be the cation, and the anion is also, most of our polyatomic anions are options as well, right? So something like SO4 2- could be the anion, for example. Metals are those cations attracted to the sea of mobile electrons by non-directional electrostatic forces. So the fact that the forces are non-directional makes them malleable, ductile, gives us the ability to change the shape of the metal pretty easily. And metals and any alloys of metals would apply to that. So again, if you look at your periodic table, you can do a pretty good job of figuring out which type of substance is going to be formed. Remember, there's that line between metals and nonmetals diagonally along your periodic table. Okay, next let's get to these key first exercise. Take a second to see which of these you can categorize in your own, and then I'll show the solution. Okay, so going through the solution here, NaNO3, when you look at that, the first thing to note is that I have Na, which is a metal on the left-hand side of the periodic table, but it's not just a metal. I also have NO3, which you should recognize as NO3 minus, the nitrate anion. So because I have a metal, which is going to then be a cation, that's the Na plus ion, and NO3 minus, that's our anion, this makes it an ionic compound made up of ions. Again, anytime you have a metal and a nonmetal together, it's going to be ionic. Calcium, if we look at where it is on the periodic table, it's on that metal side of the periodic table. So that will be a metal. And you have metallic bonding. SO2, if we look at it, has a Lewis structure here. So this is a molecular compound. There's just these sort of SO2 molecules. They're going to be attracted weakly by intermolecular forces, but we can identify specific molecules here. It's all nonmetals, and it's something we can draw a Lewis structure of, so molecular. SiO2, on the other hand, I'm showing you the picture of it here. This has this extended bonding in all three directions. I can't pick out a specific molecule. It's not like there's one SiO2 molecule right here, and then this is another one. No, they're all connected together. So that's the case where you have a covalent network solid. KCl, we look at the atoms that's made up of. K is a metal, and Cl is a nonmetal on the right-hand side of the periodic table. So again, that's going to be an ionic compound because we've got a metal, which will be the K plus cation, a nonmetal, which will be the Cl minus anion, and that makes it ionic. Brass is this alloy of Cu and Zn. So these are both metals, so that's just going to create metallic bonding. That's another property of metals, is that we can form alloys of them because it doesn't really matter which metal we put in there. I mean, it will affect the properties, but we can actually make alloys of a ton of different metals to make metallic substances with different properties. Paraffin wax here, CH3, CH230, CH3. This is, if we look at it, all nonmetals, so that's going to put us into either a molecular or a covalent network substance. If we think about which one it is, this is, even though it's a big molecule, it is just discrete molecules. We can say we've got a single paraffin wax molecule, and then what can we do? We can take and put another one next to it and just sort of keep lining up paraffin wax molecules in all sorts of different places. And again, it's going to be attractions between these paraffin wax molecules that give rise to the properties and forces. So this is molecular. Okay, here's our summary of the properties of solids. Another sort of view of that same sort of table with more information about their different properties. Okay, next exercise, again focusing more on those properties. So take a minute to see if you can do this one, and then I'll show the solution. Okay, so this one, it's we have melting points as well as these conductive properties. So maybe the conductive properties are a little bit easier as a place to start. So A does not conduct electricity, and D do not conduct electricity, whereas C does conduct electricity in the solid state, and B only conducts in the liquid state. So B, sort of right away from that given information, if it only conducts in the liquid state, that's the case for an ionic compound. Remember, since those are made up of those ions, positive and negative, when they're locked together in the solid, that's typically not conductive. The ions can't move, but once we form a liquid, these positive ions can flow, negative ions can flow, and we get a conductive substance. For some other ones here, now the other conductive one, C, is conductive in the solid state. So that one, now let's think. The only ones that are typically conductive in the solid state are metals, right? So that would be metallic bonding here. Some covalent network substances are conductive, but it's pretty rare. So C definitely fits the bill there. Notice that both of these have pretty high melting points. That's typical. Ionic compounds do typically have pretty high melting points. Now, A and D here have to be molecular or covalent. Here, they both don't conduct electricity, so the key difference is the melting points. So if we look at the difference here, D has a low melting point, A has a high melting point. The high melting point is typically going to be covalent network bonding. So this has a much higher melting point. That's going to be because it's held together by much stronger forces. So remember, covalent network solids are held together by strong covalent bonds. Then to melt the substance, we have to overcome those strong bonds. So that's why we have a high melting point for covalent network solids. Then our last one here is what's left over. That's D. Again, molecular solids are typically held together by relatively weak intermolecular forces. A typical, you can think about water as an example of a molecular solid with a melting point somewhat near 150 Celsius. Diamond would be a typical covalent network solid, much, much higher melting point because it held together by much stronger forces, those full covalent bonds. Here's that summary slide again with the key information from this first part of our material. Our previous problem, we used melting point as a key indicator, so let's look at the rest of our phase changes as shown here. An example to start with here, if we pull a block of ice out of the freezer, we've got a nice thermometer in it. We'll put that ice on a hot plate on high. What do you think is going to happen to the temperature of that ice over time? You can label it, let's say, the initial temperature from the freezer is about negative 20 degrees Celsius, say, a nice cold freezer. Okay, so hopefully you had a chance to try to see what that looks like. Well, we start out with that block of ice at, say, negative 20. What's going to happen is the temperature is going to start increasing, right? But it's not going to keep increasing indefinitely, right? At a certain point, we're going to get to 0 Celsius where the temperature is going to flatten out. It's going to flatten out while that solid transitions into a liquid. So the ice is in this beaker on the hot plate. Now it's melting and it's going to the liquid state. Remember that the temperature stays the same while it does that solid to liquid phase transition. So here we have solid and liquid, and now we're going to go back and have pure liquid here. The liquid's going to keep going. Eventually we'll get to 100 Celsius. At 100 Celsius, it's going to then go from the liquid to the gas phase. And if we were able to keep going, so this is liquid gas, we've got the boiling point of water here. The water stays at exactly 100 degrees Celsius during that phase transition, and then it's going to start increasing again. If we were able to keep measuring it, now we would have just gas left once we got above 100. So this gives us an example of some of our different phase changes, some of the properties here. The temperature stays constant during a phase change. We can also think about the energy that we're adding. So the length of time it takes, if we leave our hot plate on high the whole time, the length of time it takes is a measure of how much energy it takes to go from solid to liquid and liquid to gas. Here's an example of what that looks like. This is now putting on the x-axis heat added. So it takes just a little bit of heat to go from solid to liquid, but we have to add actually a ton of energy to go from liquid to gas. That's pretty typical that it takes a lot more energy to boil something compared to melting it. We'll see why in a little bit. Now, the different phase changes involved here. So this is one of the key things to memorize from this content, just the names of these different phase changes. Here on this graph, we have them on a sort of energy axis. So the energy of the solid is the lowest of all of our different phases. Remember, as we cool things down, we eventually go to the solid state. Liquid is a little bit higher in energy, allowing these particles to move past each other. Gas, highest in energy still. We can see that the energy changes are sort of additive here. It takes a little bit of energy to go to the liquid, some more to go to the gas, and it takes this whole amount of energy to go liquid straight to gas. The names of the phase changes: melting or fusion to go from solid to liquid. Freezing is liquid back to solid. For liquid to gas, condensation is gas to liquid. And then liquid to gas, there's a lot of different names for different processes, but the one that we use is vaporization. So that applies to all the different liquid to vapor transitions that we might also use the words evaporation or boiling for. Then solid to gas and vice versa. So gas going to solid is deposition, solid going to gas is sublimation. So again, that liquid to vapor, evaporation and boiling are words that we would use. They have technical meanings in different situations. So evaporation only occurs at the surface of the liquid. If you leave like a puddle in a classroom or something like that, that puddle will eventually completely evaporate. But we couldn't use boiling to describe that word. That water puddle is just evaporating. Boiling only happens when the vapor pressure of the substance is equal to the atmospheric pressure. In that case, we can get boiling, these big bubbles of gas forming throughout the liquid, as opposed to only off of the surface, like when we have evaporation. So they're different sort of phenomena. Boiling point depends on the pressure of the atmosphere, but the normal boiling point is the boiling point when the atmospheric pressure is 1 atmosphere. The next property, again, we talked about vapor pressure on the previous slide. Well, vapor pressure is a property of the substance and the temperature. So if we put a liquid in a sealed container here, eventually what's going to happen is we're going to get that evaporation. Evaporation, because it's a constant surface area, will be going at a roughly constant rate. And then what's going to happen is once we have a bunch of gas, we're going to eventually get condensation to start coming back down. Eventually those two rates are going to be equal, and we'll reach the equilibrium vapor pressure. That doesn't depend on the amount of liquid I have in my container. It's just a property of the substance and the temperature. So we can make a graph like this that shows the vapor pressure of 3 different substances versus temperature. It's always the case that vapor pressure increases with temperature. As we increase the temperature of liquid, we make it easier for those molecules to escape and go into the gas phase. We also have 1 atmosphere labeled here, so you can take a second to try to do these questions, answering from the graph which substance has the highest vapor pressure and estimating the boiling points of each. Okay, so let's take a look at that. Hopefully you've paused and had a second to try this. Which substance has the highest vapor pressure at 0? Well, if I go to a temperature of 0, the only one that has a significant vapor pressure is A. Just reading it off of the graph. Again, the vapor pressure of A, I don't know the exact number, but if this is 1 atmosphere, this is maybe like 0.1 or 0.2. The other two are very, very close to 0. Now for substance A, what is its boiling point? That goes back to the previous slide when we said the normal boiling point is the place where the vapor pressure is equal to 1 atmosphere. So for A, it's going to be this, right where that pressure hits 1 on my graph. If I go down to the x-axis on the temperature axis, I could estimate that at about, it looks like these are labeled every 25, so it's about 25 degrees Celsius. The other one's just reading it right off of the graph. B has the next highest boiling point. That looks like it's, I don't know, roughly 75 degrees Celsius. And C, same thing. C looks like its boiling point is about 100 degrees Celsius. Note that the thing that has the higher vapor pressure, that's pretty typical, that the higher my vapor pressure is at a certain temperature, the lower my overall boiling point is going to be. So C, we might say, is like the least volatile. C, it takes the longest, I have to heat it the most to reach the boiling point, and its vapor pressure at 0 would be the lowest as well. Okay, here's some data to back up what we looked at on some of the previous slides about the freezing and boiling points, as well as the enthalpy of fusion and the enthalpy of vaporization. So note that the enthalpy of fusion and vaporization are always positive. We always have to put energy in. So fusion is melting, remember? So always have to put energy in to turn a solid into a liquid. We have to put energy in to take a liquid and turn it into a gas as well, to overcome some of those forces holding the solid together and holding the liquid together. We also said on that previous slide that typically, if we draw an energy diagram here, the solid is the lowest in energy, the liquid is in the middle, a little higher than the solid, and the gas is typically way up here. So that means typically, if we think about our arrows, delta H vap is a lot bigger than delta H fusion. And we can see that here as well. For argon, delta H VAP is about 4 times as big as delta H fusion. For Cl2, 3 times as big. For ethanol, about 8 times as big. So pretty typical here that it takes a lot more energy to boil the substance or to vaporize it compared to just melting it. There's other nice correlations here as well. Typically, the bigger delta H of vaporization here is going to mean we have a bigger boiling point. So delta H of vaporization, how much energy I need to put in to turn the liquid into the gas. The bigger that is, typically the bigger my boiling point is. You can see a nice correlation here. Argon has the least delta H of vaporization, least energy I have to put in, and so it has the lowest boiling point. We'll look more at that in our next content area on intermolecular forces. Solid vapor equilibria. So something like iodine here sublimes at room temperature to make this nice deep purple gas. Also a very common type of situation, these solid vapor equilibria. Solids also have an equilibrium vapor pressure at a certain temperature, so that's a property of solids as well as liquids. Freezer burn is another sort of real life example where you can see water recondensing and refreezing on the packaging here, causing your frozen foods to start to deteriorate over time. Okay, our last problem here, naming each phase change. Take a few seconds and then I'll show the solution. Okay, most of these should be pretty familiar. A few of these terms a little bit less so, but I'll put them down. First 3 here, solid to liquid is melting, solid to vapor sublimation. Vapor to solid deposition, that's sometimes the hardest one. You can think about depositing the vapor onto that solid surface. Vapor to liquid is condensation. The other harder one here is liquid to vapor. That's vaporization. Don't put evaporation or boiling there. Remember, vaporization is sort of the general term that applies to whether it's evaporation or boiling. Vaporization is the general name for that phase change. Liquid to solid would be freezing. One other point I didn't make earlier, you can use fusion for melting. That is another acceptable name. A little bit old-fashioned, but nothing wrong with that. Here's the key summary slide, and that's the end of this set of notes. A phase diagram is a great way to summarize all the information about how a substance behaves at different temperatures and pressures, sort of a map for what kind of behavior you should expect to see. On the y-axis in our class, some people orient their phase diagrams differently, but in our class we're going to always use the pressure on the y-axis and a temperature on the x-axis. And what we're mapping here is the different regions correspond to the different pure phases. So we have pure solid at temperatures and pressures described by this region, the lowest temperatures, and again from low to relatively high pressure. As we move to higher temperatures, we get to the liquid phase. Eventually at high enough temperatures, we get into this gas phase. Note that there's this interesting fact that if we're at a low enough pressure, we go directly from solid to gas. We only see deposition and sublimation. There's no liquid that's stable if the pressure is too low. Some other key points on this diagram are those lines. So the lines are where the phase transitions occur, or phase changes. So any of these lines, again, this yellow one I'm trying to highlight here, it's hard to show up, but that yellow is where we see deposition and sublimation. Those phase transitions occur. Along that line is where solid and gas are in equilibrium. Similarly, again, if I go here, this is where liquid and vapor, or liquid and gas, are in equilibrium along that line. That's where the phase transitions, vaporization and condensation occur. And similarly for the solid-liquid line here, that's showing where freezing or melting occur. Now, the other two key points on this graph are this T here. That T is referring to the triple point. So the triple point is right down here. Again, this is the place where the solid, liquid, and gas are all in equilibrium at the same point at the same pressure and temperature. There's only one spot on the diagram where we can have all three in equilibrium with each other, and that's the triple point. Another key point here, if we keep looking, is this point C up here. That's the critical point. And what we notice is that above the critical point, we no longer have a distinction between liquid and gas. They're both just sort of a generic vapor phase, that if we are up here, it's a liquidy seeming vapor, and then as we go here, it just smoothly becomes more and more gas-like. But if we're above this critical point, we don't see a phase transition. We don't see a vaporization, two distinct phases in equilibrium. It's just a smooth, continuous transition from one phase to the other if we're above that critical point. Going back to our phase changes, so again, we talked about normal freezing and boiling points. Those normal freezing and boiling points are when the pressure is 1 atmosphere. So we can see those points on this graph. We find where P is equal to 1 atmosphere and then read off to the x-axis. That's going to show the normal freezing point, or the normal melting point equivalently. And then again, we go all the way across from the liquid to the vapor phase equilibrium. So this is where boiling occurs at normal atmospheric pressure. We can also really easily see things like, hey, what happens if we go to a higher elevation where we have a reduced atmospheric pressure, right? That's just drawing a different line in this diagram. Hey, this is what's going to happen. Not much change to the freezing or melting point, but we'll see a very big difference in the boiling point as we drop the pressure. Okay, this is that key information about the triple point and the critical point. One nice thing to know is that the point C there above that, we can call the phase there a supercritical fluid. Again, where that we have those smooth transition between liquid and vapor properties up there. Okay, so here's one more sort of thought experiment. Let's say we have our block of ice here, and we envision sort of a fishing line with two heavy weights at either end, and use that fishing line with the heavy weights to put right through the ice and see what is going to happen over time with the heavy weights on the fishing line. So take a second to think about what you think might happen. Okay, so it turns out for water, you will see that those heavy weights slice right through the ice. It turns out that if you think about what those weights are doing on that very small amount of area, is they're increasing the pressure dramatically. Remember, pressure is force per area, so we're putting a significant force on a very small area, increasing that pressure, which will melt the ice, and you'll actually be able to sort of slice right through the block of ice with that. You wouldn't be able to do that for most solids. That'll only occur because when we take a solid, water, and increase its pressure, it does liquefy. That's because water has the unusual property that the liquid is denser than the solid. Normally what increasing pressure will do is turn the liquid back into the solid. Normally we wouldn't be able to cut through a material in this way. People also talk about this as an explanation for why ice skating works. You're applying that huge amount of pressure on the thin metal blade. It turns out that that explanation isn't wholly accurate. It would only let you sort of ice skate down to only a few degrees below freezing, and people can ice skate and ski at much lower temperatures than that. But again, it is a key fact about water that makes it unusual from other materials. So the key conclusion is down here. Increasing the pressure always favors the denser phase. So if the solid is denser, then this line is going to be sloped. Again, just to highlight it here again, it'll be sloped slightly positive. So that'll look sort of like this with a slight positive slope on the solid to liquid equilibrium line. If it's more like water, that line will have a slight negative slope. And therefore, again, we see the behavior for water, where increasing pressure actually turns the solid back to the liquid. Okay, so one final exercise on phase diagrams. Take a minute to try to complete this, and then I'll show the solution. Okay, so here's the solution. first describe the phases or phases that are present, I'd always encourage you to first label each region of the phase diagram. It's pretty straightforward. At low temperatures, we have the solid, medium temperatures, liquid, high temperatures, gas, what you expect from elementary school. Again, we can do that to both diagrams here, solid, liquid, gas. Then to figure out what's present at each point, we just look at the diagram. So A happens to be that special triple point. So A is where solid, liquid, and gas are all in equilibrium because it's touching each of those regions. B is right in the liquid phase, so that's liquid. C is in the solid phase. D is in the gas phase. E happens to be on the equilibrium line. So that's where we have an equilibrium between liquid and gas. So we could have liquid and gas or some combination present. F, if we look at it, is on the solid to gas equilibrium line down here. So this is going to be solid and gas. Going over to the other diagram, G again is the triple point, solid, liquid, and gas all present in equilibrium. H happens to be on the solid to gas equilibrium line. J is just in the solid, and K is in the gas. Next, for part B, what phase transitions occur at points E, F, and H? So point E is on the liquid to gas equilibrium line, so that's just asking us for E, what is the name of the liquid to gas phase transitions or phase changes? Liquid going to gas is called vaporization. Not boiling. Boiling is specifically when we're at 1 atmosphere pressure, but in general it's called vaporization. The other gas going to liquid is called condensation. Okay, then F is solid to gas. Again, that's sublimation and deposition. One that's a little bit harder to remember the names of. And the final one here, H, that's the most common, easiest words. So the easiest there would be freezing and melting. For the last part C, which is denser, solid, or liquid, the easiest way to think about that is we think about starting at low pressure and visualizing cranking that pressure up by doing that experiment where we press down. So in this case, if you look at it, this line is pointed slightly to the right. So the liquid, if I go straight up, again, it's very close to straight, but you can sort of see it. If you go straight up there, you are going to go from liquid into solid. So in this case, remember that whenever we increase pressure, we're favoring the denser phase. So for the left, the solid is going to be denser. On the right, we have the exact opposite. Here, if we think about cranking up the pressure, we're going to go from solid to liquid. So that's the case where we can actually melt the solid by increasing pressure, just like water. So that is the liquid denser case. Here's all the information in that solution for phase changes just written out here. So that's the end of our phase changes and phases of matter and phase diagram content.